Now that we've seen the benefit of implicit differentiation, let's try looking at some examples using it, and we'll also revisit some classic calculus examples using implicit differentiation, so equation of the tangent line and things like that. So first up, I'm going to find y prime for the relation sine of xy equals x plus y. And remember I said earlier, how would I even take the derivative, or how would I find y prime if I don't know how to solve for y? Because, boy, I don't know how to solve for y in that equation. There's really not a good way to do it. So really, if I want to find the derivative, if I want to find y prime, no other way to do it other than to use implicit differentiation here. So this side right here, let's actually, let's start with this side over here. I think that's going to be the easier side. So I'm just taking the derivative of each side. Derivative of x, we're gonna start on that right-hand side. So the derivative of x, that's just going to be 1. Derivative of y, so the derivative of y would be 1 times derivative of y as a function of x, so times dy over dx, or you can use y prime, whatever your preferred notation is, so times y prime, because remember we have f of u times this is our u prime. We're using the chain rule here every single time. I think I'm going to use dy dx though, so times dy dx. So the right-hand side isn't too terribly bad. It's this side right here that's going to cause us a problem. So let's just look at that off to the side. Sine of xy. I see these parentheses and I'm a little worried, because I think that's going to mean we're going to have a chain rule here, because I have a function which is xy. I shouldn't say a function. I have a relation, xy, inside of another function, sine. So I need to take the derivative, and I'm going to need to use the chain rule here. So maybe I'll do this just off to the side right here. So we're working with, let's just call this, f is equal to sine of xy. Let's just look at that part separately for now, and then we'll come and revisit the left half of our problem later. So u, that inside part, that's going to be xy. U prime, when I go to take the derivative, and oh boy. Guys, look at this here. X times y. I have a function of x, which is x, times a function of y, which is y. This is actually a chain rule and a product rule. It's a double whammy. So I'm going to have to find the derivative of x times y. So u prime, first I'm going to start with the derivative of x. Derivative of x is just 1 times y. I'm going to leave that alone, so 1 times y, plus, this time I leave x alone, so plus x, times the derivative of y. Well, we said earlier that the derivative of y is 1 times dy dx, or simply just dy dx. So I'm going to say times 1 dy over dx. Then, of course, maybe we simplify this. We kind of just make it look a little bit nicer. This is really y plus x dy over dx. There's my u prime. So, okay, I'm done with the product rule. Still got to finish up my chain rule here. Let's rewrite this using u. F is equal to sine of u. So f prime is equal to derivative of sine, that's going to be cosine of u times u prime. So f prime, this is equal to cosine of u. U we said was xy, times u prime times y plus x dy over dx. So that was all just to find the derivative of this guy right here, sine of x times y. So when I go to talk about the derivative of this side, I can just go ahead and plug in the expression that I found over here. Cosine of xy times the quantity x plus, or excuse me, y plus x dy over dx. So the derivative of that left-hand side is cosine of xy times y plus x dy over dx. And I want to find y prime. Well, y prime is really just another way to write dy over dx. So really what I want to do is I want to solve for dy over dx. That's what I'm trying to do here. So there's not a great way to do it. We're going to have to do a little bit of algebra here. On the left-hand side, I'm going to take cosine of xy, and I'm going to distribute it here. So I'm going to say, let's say cosine, actually, I don't like it. You know what? I'm going to rewrite this. I think that looks kind of ugly the way it is. I'm just going to switch the order that these two are being multiplied by. Let's fix that up here. I apologize. But I think this is going to make the problem a little bit easier. So we'll say y plus x dy over dx times cosine of xy. There we go. All right, so now I'm going to go ahead and distribute this cosine of xy. So I'll have y, let's stick with blue, y times cosine of xy plus x dy over dx cosine of xy equals, on the right hand side, I'm not going to do anything over there. I'm just going to say that's 1 plus dy over dx. If I'm trying to solve for dy over dx, I should probably get those on the same side of my equation. So I think here's what I'm going to do. I'm going to take this term over here, subtract it, we'll move that over to the right-hand side. And then this term over here, I'm going to subtract it, I'm going to move that over to the left-hand side. So once I do those two things, I'll have x dy over dx times cosine of xy minus dy over dx is equal to 1 plus cosine of xy. Oops, you know what? Ooh, I forgot my y. So let's fix that. I forgot the y in front of the cosine. Plus y cosine of xy. At this point, I see, okay, here's my dy over dx, here's my dy over dx, and really what I've got is I've got two terms. I've got here's a term and here's a term. So I can factor out that dy over dx. So dy over dx, it's going to leave me with x times cosine of xy minus 1 is equal to 1 plus y cosine of xy. Well, again, keep in mind what we're trying to do. We're solving for dy over dx. So my last step, I'm just going to divide by x cosine of xy minus 1. So dy over dx is equal to 1 plus y cosine of xy divided by x cosine of xy minus 1. So there is my derivative. Whew, holy moly. So while implicit differentiation is nice, it's not all sunshine and rainbows over there. Like, there's still going to be hard problems. Here we had a chain rule and a product rule. The algebra was yucky. It just wasn't it was a tough problem. So you're still going to run into tough problems using implicit differentiation. So let's look at a couple more examples here. The rest of these, I think, are going to be a little bit nicer to work with. That one was very challenging to solve for y prime, or to solve for dy over dx. Here I just want to kind of talk about this bullet point. It says derivatives found using implicit differentiation typically depend on y and x, so we need an ordered pair to find the slope of the tangent line. So we have to have this ordered pair. We will generally need both an x and a y value if we're going to find the slope of the tangent line using implicit differentiation. So I have x squared plus xy minus y cubed is equal to 7. And I want to take the derivative. So okay, derivative of x squared, that's going to be 2x. Derivative of xy right here, I've got a product rule. Anytime you've got a power of x times a power of y, this is going to be a product rule. So, okay, let's handle these one at a time. And actually, let me just give myself a little bit more room. So 2x plus derivative of x. Derivative of x is 1 times y. So that'll be times y. Plus, this time I leave x alone. So x times derivative of y. Well, the derivative of y is just dy over dx, or 1 times dy dx. And here is my product rule. That's it. So, okay, I still need to take the derivative of negative y cubed. Let's do that. That would be minus derivative of y cubed. That would be 3y squared times dy over dx using our chain rule. Derivative of 7 over there on the right-hand side, that's just going to be 0. So let's see, I have 2x plus y plus x dy over dx minus 3y squared dy over dx is equal to 0. So I want the equation of the tangent line. I have the x value, I have the y value, I need the slope, which means I'm looking for the derivative, which in this case is dy over dx. So I'm trying to solve for that. I'm going to move these two terms over to the other side so that I can isolate dy over dx. So x dy over dx minus 3y squared dy over dx is equal to negative 2x minus y. Again, I can factor out dy dx on that left-hand side. That's what I want to do. So dy over dx. That leaves me with x minus 3y squared is equal to negative 2x minus y. And then to solve for dy dx, I just need to divide by that factor of x minus 3y squared. So dy over dx is equal to negative 2x minus y over x minus 3y squared. Okay. So we have the derivative. I think finding the derivative here in this problem, that's the hardest part. Once you have the derivative, it should be downhill from here. Because what comes next? Remember, the thing I'm after, the thing I'm trying to find, is the equation of the tangent line. It's the equation of the tangent line. I need the slope of the tangent line. So I'm going to take my ordered pair, I'm going to plug that into my derivative. Take the x value, I plug it in for x. Take the y value, plug that in for y. So let's do that. I'm just about out of room at the bottom. So let's say dy over dx is equal to negative 2 times my x value of 3 minus y, that is 2. All over x is 3 minus 3 times 2 squared. And we're going to evaluate this. So negative 6 minus 8 all over 3 minus 3 times 4. I've got what? Negative 14 all over 3 minus 12. This is really negative 14 over negative 9, or just 14 over 9. Kind of an ugly number, but we'll deal with it. So this is, remember, the slope of my tangent line. That is m. So my last step here, I've got my ordered pair, I've got my x value and my y value, I've got my slope. Let's write the equation of the tangent line. So let's see, let's do that right here. Y minus my y coordinate, what is that? That is 2, equals m. We said that was 14 over 9 times x minus my x coordinate. That would be 3. Then I take this and solve it for y. By now, I think we know how to do that. This video's already been pretty long, so I don't want to take it any further. But from here on out, we're just going to take this, solve it for y. And that's the end of our problem. Oops.